Sweet, it works. Okay. Yep. I can see it myself. Thank you for letting me know. So how this review is going to work, I'm going to just run through a bunch of problems and explanations for different subjects for the class. If you have any questions, you can post in the YouTube stream chat, which I can see. I'm also sitting in a Discord call in the IEEE, Discord. So you can join that and verbally ask questions too, which is preferable since I'll be looking down a lot and not the YouTube chat, but either one works. So first of all, I have no idea what's covered on your test, your midterm. I'm guessing it's everything up to first order circuits. So that would include stuff like, we'll call them basics, and then move from basics onto node voltage, mesh current. That's not how you spell mesh. Mesh current, superposition, source transformations. Yes, this will be recorded and posted. I think automatically, actually. So yeah, right after this is over, it should be all going up. Thevenin equivalence. And then, well, capacitors and inductors, basic properties of that, and then first order circuits. So this is what I think will be on your test. Am I right or am I wrong? And if I'm wrong, that's fine. I mean, if I'm wrong, that's fine. This stuff, I doubt I'm going past the material this late in the semester. In that case, I'm going to start up with going over some of the basics. Let's quickly get started through those. Some background information. So stuff we're interested in. We're interested in finding for all these circuits, right? We want to know the voltage. We want to know the current. And we want to know the power. The power can be related to the voltage and current, as power equals voltage times current. And using Ohm's law, you can rearrange this into various forms. Something important with power is called the passive sign convention. And if you have a circuit element that has some voltage drop across it, we'll call V. If the current is going into the positive terminal, the convention is to call that power positive. All right, so this is positive power. However, if the current is going into the negative terminal, the convention is to call this negative power. This is I. This is just, it doesn't really matter which way you do it, but for the purpose of I think the textbook and most people, this is the convention. What does this negative and positive power mean? Well, in these linear circuits, power is conserved, which means the sum of power equals 0. Also, something to note is that resistors will always absorb power. And absorbing power relates to a positive power. A negative power means you are delivering power to the circuit. So this would be in the form of circuit elements such as voltage sources and current sources. Although something that's important to note is that sources don't always have to give power. Sources can absorb power too. But resistors cannot. Resistors cannot give power. They have to absorb it only, right? So speaking of those sources, there are two main types of sources, voltage and current. Each of them comes in two different flavors. We have the independent sources and the dependent sources. A voltage source keeps a constant current. A voltage source keeps a constant voltage between its terminals, no matter what current is in between it. A current source is the opposite. It keeps a constant current between its terminals, no matter what voltage is across it. What makes a dependent sources different than independent is that if the voltage source is a voltage V and a current source ideally is a current I, the dependent sources are dependent on some other function of the network, which is usually a current or a voltage. So their value, well, whatever this value turns out to be, it will stay fixed across the terminals. It depends on something else, which is why it's called dependent. Some important things to note is how sources behave when you cascade them and put them together. So, for example, if I have a voltage source like this, we'll call it V1. If I have a voltage source like this, we'll call it V2, and I wire them in parallel. Can we do this? Yes or no? Well, if V1 equals V2, check mark, it works. If V1 doesn't equal V2, bad. Basically, in real life, this condition would never happen, right? So this would blow up. Don't do this. This is bad. However, something that's much more reasonable is, let's say we have, again, V1, but this time it's in series with V2. That's right, Jeremy. Boom. Then we can add them up into one current source that just takes the cumulative effect of those terminals. Similarly with current sources, a similar effect happens. If we have current sources, let's say they're in series, I1, I2. If I1 does not equal I2, we have major issues here. So don't do this. This also goes boom. However, if these current sources are in parallel, and I'm sure you can guess what's going to happen, they're going to add up to one aggregate current source. This I1 is I2, this is I1 plus I2. Something helpful something helpful just to keep in mind when you're dealing with these sources. So let's talk now, we'll move on. Let's talk about some basic laws, Kirchhoffs laws. So first I'm going to talk about Kirchhoffs voltage law. Kirchhoffs voltage law states that when we're going around a closed path or a loop, so let's say we have a bunch of circuit elements, and all these elements, doesn't matter what they are, they have some voltage across them, right? I'll put it like this, just for demonstration purposes. We're going to say if we go around the loop, the sum of voltages must be 0. Okay, well, let's ask an interesting question. What is a positive voltage and what's a negative voltage? The convention I use, personally, is that if you're going around and you encounter a voltage drop, that's positive, and a voltage rise is negative. This is counterintuitive, so you might not want to do this. But the reason I do it is because you encounter more drops than rises, so it's easier on your math. So, for example, if I was doing this one, going on a loop counterclockwise, the sum of the voltages is going to be, let's start with V4. V4, I see a voltage drop, positive. V3, I see a voltage rise, negative. V2, I see a voltage drop, positive. V1, voltage rise, negative. And note that you could easily switch it all around. If your convention is different, let's say you want to use the convention of drops being negative and rise being positive, go for it. Just stay consistent. I'm just going to be using this one from now on. Similarly, for Kirchhoffs current law, KCL, it states that the sum of the currents going into and out of a node are 0. So what is a node? A node is where two or more circuit elements meet. So theoretically, there'd be elements at these sides, but I'm not going to draw them. We're going to have I1, I2, and I3. My convention is that currents going into a node are positive, and currents going out are negative. So I will write this as sum of the currents equals I1 going in. Oh, actually, let's make I3 going out. I1 going in plus I2 going in and minus I3 going out. And that's going to equal 0, according to Kirchhoffs current law. And then you could use the opposite convention as well, or you could not. Just make sure you're consistent. All right, let's talk about now what are these components we're talking about. I've drawn them as boxes, but we're actually working with resistors, capacitors, and inductors. So let's focus on resistors. A resistor is a circuit element which is defined by its resistance. Ohm's law gives us that the current and voltage across the resistance is related by V equals IR. Very handy. Resistors combine in multiple ways, two main configurations. If they are in series meaning that the same current flows through each element. Basically, they're all in a line with no interruptions. So R1, R something, all the way to Rn. You can have like n resistors in series, right? If there's no branches off of it, like this would make it not all of them not in series. If there are no branches, they're all in series. And you can combine them into one equivalent resistance, R equivalent. So for resistors in series, R equivalent is the sum of all resistances. Very nice and easy. And of course, the same current is going to flow through all these branches, right? So this is series. For resistors in parallel means that the elements, or resistors in this case, both start and end at the same node. So if we have a node here, and we have a resistor that starts at node A and ends at some node we call B, we notice that these other resistors also start at node A and end at node B. So if we have RO and we have RN, this can be combined also into equivalent resistance. The defining feature of resistors in parallel is that the voltage across them is the same. So for series, they have the same current through all elements. For parallel, same voltage through all elements. To find this R equivalent for the parallel resistors, I'm going to define it as 1 over R equivalent equals the sum over all resistors of each resistance. And then you'd find this formula and do some algebra to actually compute the resistances. All right. In the book, at least the book I use, they also cover delta Y networks. I rarely see this as a topic in ENA classes. The biomedical classes cover this a lot, but ENA rarely does. So I'm going to skip it. So I'm sorry if you guys actually use this circuit configuration. So let's talk about something else now. With these resistors in series and parallel, we can lead to some special configurations that we like to take advantage of. One of them is the voltage divider. The voltage divider is the way to find the voltage across resistors in series. So like before, resistors in series, we had a bunch of these resistors, right? We had, R0 and then all the way up to Rn. And we had, we knew we had some current going through them. But what if we want to know the voltage across each one of these resistors? Well, if you know the current, you can just use Ohm's law, right? Let's say you don't know the current. Let's say you know some voltage across the entire set of resistors. Then what is the voltage drop across each individual element? That is what the voltage divider formula tells us. It tells us that for the voltage across any resistor I, it's going to equal the total voltage times that resistor over the equivalent resistance of the entire sum in series. What this is most often presented is a special case where there are two resistors in series with some voltage source like this. This is where you'll most often see it. So R1, R2. So let's say you wanted V1, which is the voltage across R1. Then you'd say V1 equals the total voltage times its resistance, so that's R1, over the resistance equivalent, which is, following our formula for resistance in series, R1 plus R2. And you'd solve for V2 in a similar manner. There's also a current divider, where for resistors in parallel, we know that the current divides itself up among each branch. So if you know the total current going into a parallel configuration of resistors, to solve for the current going through any one resistor, let's call it IK actually. II is kind of confusing. We'll say IK equals I total times the opposite of the voltage divider. This time R equivalent's on the top and RK is on the bottom. Right? And like the voltage divider, a special case is with two resistors in parallel. So you have some total current I and resistor 1 and resistor 2. R1, R2, and I. Let's say you want to know I1, which is the current going down here. Following our formula and doing some algebra, I'm just going to write down the answer that I1 is going to equal I times R2 over R1 plus R2. If you apply this, you'll find they're the same. And then I2 would equal I times R1 over R1 plus R2. All right, so these are things to keep in mind, and they help you with solving things very nice and quickly. So these are helpful for small scale analysis. But if we have an enormous circuit and we want to find out the voltage and current and power throughout all the circuit, we'll have to use some more special techniques. The first one covered is the node voltage method. This is a circuit analysis technique based on KCL. So you kind of need to know KCL to do this. The steps I take for node voltage. Step 1. I'm going to ID all my essential nodes. And that means nodes that I can't get rid of. And I get rid of them by combining components when possible. To make my life easier. Okay. Step 2. I'm going to choose a node as ground. I'm going to assign that node as voltage 0. 3. I'm going to write KCL equations for the other nodes in terms of voltages. Now, how do we do this? Let's say I have some VA, VB, some R here, right? And let's say that I'm saying the current's going this way, right? Then I can write that I equals the change in voltage over R across resistor R. And I can write this as the starting point minus the ending point over R. And this depends on which way the current is flowing, obviously, right? And you do this for each node in the circuit that's not the ground node. And then 4, you're going to solve your system of equations that arises for each voltage. And then you have the voltage of every node in the system. And from that, you could solve for any other element you wanted. As an addendum, 4.1. If you have dependent sources in the network, you can want to express each one in terms of node voltages. And once you've done that, you can solve for the node voltages as possible. You'll still have a nice system of equations to solve, right? Also, quick note on these currents. You can define your currents going any way you want. It does not matter, as long as you keep it consistent. So I would recommend drawing your currents in when you actually solve these. So as an example, let's solve a circuit using node voltage. So here's example 1 for the node voltage method. Let's say we have a circuit that looks like this. This is 100 ohms. This is 300 ohms. 100 ohms. 200 ohms. 6 volts. 12 volts. All right, here's the circuit. So following our steps, the first thing we want to do is combine resistors when possible. These two resistors are in series. So I'm going to get rid of them and combine them into one total resistance of, it was 300 plus 100, 400 ohms. Right? Now I'm going to label our nodes and call it node A, call this node B, call this node C, call this node D. I'm going to set D equal to ground because it's the smartest choice here, right? And then we're going to I'm going to draw in my currents so I don't forget where they're going. Just to illustrate how it doesn't matter how you draw your currents, I'm going to say I1 is going this way, I2 is going this way, I3 is going this way. Is this possible? No. You can't have every current going to the node, right? That's just not possible. But what will happen is one of these currents will turn negative, meaning that its true direction is opposite, and then you'll have some proper flow going on. So it does not matter how you define them at all, as long as you stay consistent. Which is why I draw them, so I don't forget. Okay, let's write some equations. Starting at node A. Well, node A is really VD plus this 12 volt voltage source. VD is 0. Node A is 12 volts. No fancy equation required. All right, let's look at node B. No KCL required, right? Let's write our KCL now for node B. At KCL node B is I1 plus I2 plus I3 equals 0. But we can write these in terms of node voltages. So for node B, I1 is voltage at A minus the voltage at B over 100 ohms. I2 is a voltage at D. No, sorry, I2 is the one on the top right. I2 is a voltage at C minus the voltage at B over 400 ohms. And I3 is the voltage at D minus the voltage at B over 200 ohms. And that equals 0. All right, let's look at C now. C. Like A, C is VD plus 6 volts, which really equals 6 volts. Right? So we know A and we know C. So we can plug these into our answer. A, this is 12, right? C is 6. D is 0. This equation has only one variable, which is VB. So when you do the algebra, which I assume you all can do, I'm not going to do it on here, you'd eventually solve for VB equals 54 over 7 volts. Final answer. Right? Okay, so that was an easy example just to illustrate how it works. Let's do something harder now. Example 2. Okay, let me draw this mess of a circuit. So I'm going to throw in some dependent sources now, because those are a bit hard to deal with. Or maybe they're not. Maybe it's a circuit god, right? Dependent source there. Dependent source here. And one resistor. So 2 ohms. Call this Vy. 3Ix. Here's Ix. 2 Vy. 9 amps and 2 volts. Okay, so here's the circuit. We're going to say that I didn't miss anything, right? Yeah, everything's here. So the question is obviously solve using no voltage. So step 1, combine where you can. There's nothing to combine here. You can't nothing here is in series or parallel, so you can't smush them together. So we're going to leave it as is. Next, we need to define our nodes. So I'm going to call this node A, node B, node C, node D, and here's node E. I'm going to draw in our currents. I'm going to say this current's going this way, this current's going this way, this is going this way, this is going this way. This already has a current from the current source, I'm not going to draw that one. This also has a current from the current source, I'm not going to draw that one. And this current's already defined as Ix, so I'm not going to relabel it. I'm going to choose node E to equal 0, because it's in the most convenient location for that. And now that's all done. What we want to, before we get started, let's write our dependent sources in terms of node voltages. So what do I mean by that? Well, this current source over here has its dependent term as Vy. And I want Vy to be in terms of our nodes, A, B, C, and D. So what is Vy? Looking at Vy up here, we can define that Vy equals Vc minus Va. That's perfect. We have Vy in terms of voltage. Done. What's our second dependent term? Our second dependent term is from the dependent voltage source. the dependent voltage source depends on Ix. What is Ix? Well, Ix equals VE minus VD over 2. We know V is 0 because it's ground. This equals negative VD over 2. All right, perfect. Those two are done, and we'll plug them back in later. Now let's get on with our system equations. Solving for node A. Node A equals, I didn't label these currents, did I? Let me label them real fast. I'm going to call this I1, I2, I3, and I4. Okay. Node A. Node A is I1 going into it minus I4 minus 9 equals 0, right? We can rewrite this. We can say this is negative 9 plus, what is I1? I1 is VC minus VA over 2 ohms. What is I4? I4 is VA minus VB over 1 ohm. This equals 0. Moving on to B. Node B is I4 going into it plus 2VY minus I3. This equals 0. Let's rewrite it. What is I4? Well, we had that before. I4 is VA minus VB over 1. Perfect. What is 2VY? Well, 2VY is a current. But we know VY is VC minus VA. So let's rewrite this as 2 times VC minus VA. And what is I3? Can we define I3 in terms of resistances or voltages? Not currently, right? It's going through a voltage source. We don't know what that current can be because the voltage source will work regardless of the current going through it. We also have no idea of what to put it in terms of. So I'm just going to leave it as I3 and we'll come back to it later. So we're going to say minus I3 equals 0. Okay, what about node C? Well, node C is in between a voltage source and ground. So VC equals 2 volts just by inspection. That's very nice and convenient. All right, let's look at node D. Node D is I2 plus I3 plus IX equals 0. That's I2 plus I3 plus IX. Let's write them in terms of no voltages. I2 we can write as VC minus VD over 1 because of that 1 ohm resistor in between. I3, once again, we don't know how to write. Let's just write plus I3. And then IX we have previously defined as negative VD over 2, right, from up here. And that equals 0. All right, perfect. So let's see, is this equation solvable? We have 4 equations, right? The equations are A, B, C, and D. How many unknowns do we have? Well, we have VA, VB, VC. VC is not an unknown. I'm going to ignore. Actually, it's VC and VD, right? But we also have I3 as an unknown. So we could really use one more equation to solve this. And now there are 2 ways of doing this. You could either you could notice that VB and VD are just, if you add them, I3 will cancel out. Or you could notice that you can write VB and VD in terms of each other. If we look back at the circuit, we can say that VB plus 3IX equals VD. We know what IX is. So VB plus a negative 3 VD over 2 equals VD. And this is our next equation, which I will call VB equals 5 over 2 VD when you move that over. So VB equals 5 over 2 VD. Now we have 5 equations, 5 unknowns, and using your favorite system solving method, you can solve, saying that VA equals negative 2 volts and VD equals 2 volts. Okay. Let's move on to something else. So node voltage was one method for solving circuits. The other method is called mesh current. Mesh current is in terms of Kirchhoffs voltage law, and here are the steps I use. So we're doing mesh current steps. Step 1. ID your meshes. Step 2. Define mesh currents going some direction on the mesh. So define mesh currents. As a quick note on these, define them all going one way. So either going clockwise or counterclockwise. It doesn't matter which one you choose. Just make sure to choose the same one for all your mesh currents. Then you're going to write KVL equations around each mesh in terms of the mesh currents. So like example, here's some resistor. Let's call this mesh current I1, I2 with some resistance, right? Now, this has a peculiarity. It depends on what your point of view is. Let's say you're writing the equation for mesh 1. In this case, you'd say that V equals the change in I times R across that resistor. And it's going to equal I1 minus I2 times R. Because from your perspective at mesh 1, I1 is positive. If you were writing it from the perspective of mesh 2, you'd say that let's say that V equals I2 minus I1 times R. Because if you're writing from the perspective of mesh 2, I2 is positive. Because, remember, resistors cannot give power. Their power has to be positive. So where your positive terminal is depends on what you're looking at, what perspective you're looking at. And then 4, solve system equations. And like with no voltage, if you have dependent sources, express them in terms of mesh currents and then solve. Okay. Example 1. Here is a current source. Four amps, 5 ohms. A voltage source coming in hot. Okay, so let's write our values in. 4 volts, 3 ohms, 2 ohms, 2 amps. Okay, so that's our circuit. Let's define our mesh currents now. So I'm going to say that this is I1, this is I2, this is I3, tiny, this is I4. Okay. Let's write our mesh currents, equations for each mesh. Let's look at mesh 1. Looking at mesh 1, we can see that I1 eventually runs this way in parallel to this current source, but not even parallel, on the same branch as this current source, right? So if this current source is 2 amps and I1 is the same as that current source in that branch, I1 has to equal 2 amps. Okay, let's look at mesh 2. Writing our system equations for mesh 2, starting over here and going up, we see that we have 2 ohms times I2 minus I1. Now we're at the 4 ohm one, the 4 ohm resistor. So we're still dropping power. So I2 minus I4. And then going to the 3 ohm resistor, 3 times I2 minus I3. This equals 0, where this is a change in voltage times R 2, and this is the change in voltage times R4, and this is the change in voltage times R3. And as for why they're all positive, remember I explained back with KVL that my convention is that drops in voltage are positive. If your convention was different, these would all be negative. Okay? Let's look at mesh 3. So just like mesh 1, and this branch over here, I3 runs in the same branch as its 4 amp current source. This means that I3 has to equal 4 amps. The magnitude of I3 is equal 4 amps, but it's running the opposite direction. So I3 actually equals negative 4 amps. Let's looking at mesh 4. I'm going to get, starting at that 1 ohm resistor in the top left, the voltage drop is going to be 1 ohm times I4. Now we see a voltage rise of 4 volts, which I define as negative, minus 4. We now see this 4 ohm, oh, oops, I made a mistake here. There should be another resistor over here. Let's take that resistor into account now. Plus I4 times 2. And we have the 4 ohm resistor at the bottom. I4, and this time, sorry, 4 ohm resistor, this time it's I4 minus I2 because we're looking at the mesh from I4's perspective. This equals 0. So let's look at equations. We have 4 equations. 1, 2, 3, 1, 2, 3, and 4. We have 4 unknowns, I1, I2, I3, and I4. So when you solve this using your favorite system solving method, you're going to get that I2 equals negative 0.85 amps and I4 equals 0.085 amps. And then you already know what I3 and I1 are. Okay, so let me do one more mesh current example, and then we can move on to bigger and better things. So, also, if anyone, can you confirm that your test stops at first order circuits, or do you go past that? We see it goes past that, you might want to skip this and move on to something harder. I'll wait. If you guys post anything, I'll see it. But for now, we'll do this example. Okay, and we see, so now I have some dependent sources, which will make things marginally more difficult. 50 volts here, 2 ohms. I'm going to call this V delta for use in our current source, 1.7 V delta, 9 I delta, 20 ohms, 5 ohms, 4 ohms, that's everything. Okay, let's define our mesh currents. I'll call I1 going this way, we'll call I2 going this way, we'll call I3 going this way. Oh, I delta. Sorry, this is I delta. So let's first put our dependent sources in terms of mesh currents, like I've been talking about. Let's start with I delta. I delta is up here. What's also up there? I2. So, I delta equals I2. Easy enough. Or capital I2. What about V delta? V delta is across this 2 ohm resistor. V delta equals IR from Ohm's law, right? What's the I? The I is I1. What's the R? The R is 2. Equals 2 times I1. So now both of our dependent terms are in terms, our dependent terms are themselves in terms of mesh currents. And so we can plug them back in and solve once we get to that step. Let's use KVL and write some equations. Looking at I1, I see going this way. I see a voltage rise across 50. I call that negative 50. I'm going to see this 2 ohm resistor, so that's plus I1 times 2 ohms plus this 4 ohms times I1 minus I2 and then I see a voltage drop of 9I delta, and that equals 0. Okay, oops. For our second mesh, I'm going to say that 5I2, right, starting at the top, going clockwise, plus 20 ohms times I2 minus I3. And then we'll see a voltage rise of 9I delta. So I'm going to say minus 9I delta. And then we see the 4 ohms. So that's going to be plus 4 times I2 minus I1 equals 0. For mesh 3, we can see over here the mesh runs in the opposite direction of our independent current source, or not independent, dependent current source, but still a current source, but not nonetheless. So I3 has to equal negative 1.7 V delta. So when you plug in these two values for the dependent sources, we're going to get two equations, which are these two, with two unknowns. And you can solve that. And once you solve that using your favorite system solver, you're going to get I1 equals negative 5, I2 equals 16 amps. And that's your answer. Right. So once you solve the system, then it's all easy. This math. Okay, let's move on. Moving on to superposition. What is superposition? Superposition is a property of linear systems, which these circuits are, that states that we can take all the inputs and just separate them and consider each separately, right? So if you consider a circuit as a system, or the inputs are sources and the outputs are like currents and like voltages, and the system itself is resistors, then we can take steps to separate them and solve them one source at a time. Okay, well that begs the question, how do we get rid of sources? All right, deactivating sources. Also known as step 1. So deactivating source. Step 1, deactivate all but one source. So to deactivate a voltage source keeps some constant voltage across its terminals. So if you want to deactivate it, you will want 0 volts across its terminals. That is a wire. A current source keeps a constant current across its terminals. To deactivate, you want 0 current across its terminals. That can be modeled as an open circuit. So once you deactivate all but one source, you're going to solve the circuit and find the output you're interested in for that one source's effect. Then you want to repeat 1 and 2 for every source until you use them all up. And then you're going to add up all the outputs, because every output you found was just one part of the superposition. And to get the total, you want to add them all up. Okay, so how does it actually work in practice? Let's do a quick example. Example for superposition. Let's say you have a circuit that looks like this. And has some sort of source in the middle here. 5 volts, 4 ohms, 1 ohm, 3 ohms, 2 ohms, and we want to find Ix. I guess I'll draw the ohm symbols. We want to find Ix. All right, cool. What the heck is Ix? Well, no idea. And how do I solve this in general? You could use KCL or KVL, but this is about superposition and how it can work. So let's use superposition. We're going to start by deactivating this current source. When I deactivate this current source, if you remember, I turned into an open circuit. And when I turn to an open circuit, we're reduced to just this triangle. Right? This is now an open circuit. Well, I can redraw this triangle as something like this. Let me turn to something that's more familiar to us. And if I combine, because now we can see that these resistors are in parallel, these resistors are in parallel, and they're all in parallel with that 5-volt source. So, okay, so these resistors are in series, and that series combination is in parallel with everything else. I misspoke, sorry. When you do a series combination, oh, what the heck? When you do a series combination, this is 6 ohms, and this is 4 ohms, and this is, of course, 5 volts. What are we interested in? We're interested in IX. IX is the current going through the voltage source. Solving for that in any way you want, you can combine those two resistors in parallel. You get some equivalent resistance here of 2.4 ohms, and then V equals IR. IX1, I'm calling IX1, is going to equal 2.053 amps, right? All right, step 1. Let's repeat. This time, deactivating the voltage source. Well, when we deactivate the voltage source, we get, let's see here. I don't want to redraw it. Let me use the power of technology and just copy paste it. Ah, look at that. And we're good. Okay. So let's deactivate this voltage source. To deactivate the voltage source, we want to get rid of that 5-volt thing in the middle, and that's going to be replaced with just a wire, right? Okay, so now how do we find IX? And I'm going to call this IX2, since it's under the second step we're doing. There are many ways to do this. The way I chose to approach this is, let's use KCL. If I can find this current and this current, then I'll know IX from KCL. How do I find those currents? One way is if I can find the voltage across here, I can use Ohm's law to find the currents. So I'm going to squish the circuit into a form like this. This is -3. This is 0.75, 1.33. Because now I can see that now these two are in parallel, and these two are in parallel, and they're all in series. So that's what I did to get this circuit over here. Once I solve for that, I find that the voltage across this resistor right here is, I'm going to call it the voltage 1. That equals -4. And the voltage across this resistor, I'm going to call voltage 2. That's equal to -2.25. Now, because they're in parallel, the voltage across this equivalent resistor is the same thing as the voltage across this resistor. So I can solve for I2. And the voltage across this resistor is the same thing as the voltage across this resistor. And I can solve for I3. And once I do that, using Ohm's law, I get that IX2 equals -1.25 amps. And to get our final answer, we use the property of superposition. We want to find our output as a function of both sources, and we just found our output independently with only one source active. So our total IX is equal to IX1 plus IX2, which is equal to 2.053 from what we solved up here. Plus, if this will work with me, plus what we just found over here, which is -1.25. And this gets a final answer of 0.8333 amps. And that's how you apply superposition to help you solve circuits. Okay, so another helpful technique to help you solve circuits is going to be the source transformation. The source transformation is a simple theorem that says, okay, let's say we have some circuit that looks like this. And these terminals A and B, they connect to whatever. It doesn't matter. What we say is that if we want this circuit to have an equivalent effect on those terminals, we can just turn it into something and turn something that looks like this. We can go back and forth here, and the effect over the terminals A and B is the same. And we can go back and forth by just applying Ohm's law. This I, just apply V equals IR, and then you can find the values and rearrange your circuit to the equivalent. All right, so how do we actually use this? This is kind of a one-step process, right? Well, we can use it to get things that are more favorable ways and combine things easily. Let's actually take a look at an example to talk about how we exploit this. So let's say we have a circuit with like a lot of sources. So I'm talking like 5 sources. Something like what I'm about to draw. And to get some motivation, we want to find IO, which is the goal. Here is a 15 ohm resistor, a 17 ohm resistor, 34 volts, 34 volts, 5 ohms, 1 amp, 6 ohms, 6 ohms, and 2 amps. Okay. So, how do we start? Well, first we have to define and find our pair. So we want to find things that look like one of these two, right? And then we convert them and see what that gets us. Let's identify some pairs. I spy this right here. That's a pair, right? Over these terminals. Yeah, that looks like this. Okay, perfect. What about this up here? Right, that also looks like that over the entire circuit. And then finally, what about this? This is a voltage source and resistor in series over the entire circuit. That's perfect. So I can source transform each of those 3 individually. Let's start with the blue one. The blue one transforms using Ohm's law. The equivalent voltage would be V equals IR, where I is 2 and R is 6. That's 12 volts. And then that resistor stays and it's brought up to be in series with the terminal. And then this resistor is still here. All right. What about the pink part? The pink part, well, that transforms V equals IR again. That's 5 volts with a 5 ohm resistor in series over the terminals. So let's make them in series over the terminals. That should be a 5. Okay. What about the green one? Well, the green one was a voltage source and resistor in series over the terminals. Now they should be in parallel over those same terminals. So over terminals A and terminals B, these are now in parallel. And this resistor here still exists. Okay. Terrible drawing. To illustrate what I've done here, we had blue up there, blue turned to blue here. We had green up there, green turned to green here. We had pink up there, pink turned to pink here. Okay, so now we can see this circuit actually a much more favorable spot, right? We have like 5 things in series we can combine to make one super simplified circuit. So let's do that. The 12 volt and the 5 volt circuit add up 17 volts. 6 plus 6 plus 5, all these resistors are in series to also, by a factor of major coincidence, also form 17 ohms. And then the rest of the circuit is as we drew earlier, with the 2 amps here, the 17 ohms here, and the 15 ohms here, which I'm not going to write down. So let's do some more source transformations. Why not? We can make everything more interesting and easier. This is a source transform pair. Let's transform that into something else. Let's make that a V equals IR, so I equals R over V over R, and that's 1, 17 over 17. This is a 1 amp current source going up. We still have the 17 ohm resistor from the source transformation, and everything else is still the same. So now, and I did the source transformation like blue went to blue, right? Okay, but now everything's in parallel, and since everything's in parallel, I can combine everything. So these current sources combine in parallel to make -1 amp. The resistors combine to make 8.5 ohms, and we still have this 15 ohm resistor with the IX we wanted to find. So or IO, I think I called it. And we can use the current divider equation to do that. IO equals -1, the total current, times of the other resistor over their combination is equal to negative 850 milliamps. Alright, so sweet. We have our answer, and that's how you would apply source transformations to actually solving a circuit. Let's move on to something else. The Thevenin equivalent. So the Thevenin equivalent of a circuit states that any circuit's effects across two terminals, any circuit. Let's say we have some black box. This is a circuit. It has an effect across two terminals. Don't know what it is. Well, that entire circuit can be reduced to some Thevenin voltage, some Thevenin resistance over these two terminals. Yeah, it needs to be just the entire thing. Just goes right down to, well, that. So how do I find this Thevenin equivalent? Oh, there's also another. You'll notice that this looks disturbingly similar to what we had for our source transform pair. So if we source transform this, we get the source transform effect over terminals A and B, and this is called a Norton equivalent. But once you have one, you have the other. So we're just going to talk about solving for the Thevenin equivalent. So how do I solve it? Well, you can find each of the three components, V Thevenin, I Thevenin, R Thevenin, separately by looking at certain different ways. So how do I find V Thevenin? Well, to find V Thevenin, we want the voltage across these terminals. And to do that, we're going to say, okay, what if the load across these terminals was infinite? That's like an open circuit, right? So that basically, we're going to place an open circuit at the terminals and solve for that voltage, V open circuit. And that V open circuit is V Thevenin. So that's how we solve for that. For I Thevenin, we're going to do the opposite. We're going to say, all right, what if there was a short circuit here? Then all the current from the Thevenin equivalent would go through that short circuit. And that would mean that that has to be the I Thevenin. So place a short circuit at the terminals and solve for the current through that short circuit, and that is your I Thevenin. Okay. And now, so let me check my battery life real fast. Oh, that's going fine. Okay. And then R Thevenin. So you're going to, first step for R Thevenin is, there's like sub-steps here. Deactivate all independent, that's a terrible spelling, sources, just like we did for superposition. You're going to place a test source at terminals and solve for the voltage of the test source over the current of the test source. And that equals your Thevenin resistance. Also to note, if you have two of these, any combination of two of these quantities, you can solve for the third using Ohm's law, right? So V Thevenin equals R Thevenin times I Thevenin. So really, you only solve for two, but solving for all three is a good check. Let's do a quick example. Okay, let's draw a circuit. I naught, negative 1 amp, 2 ohms, 5 ohms, 6 ohms, 3 volts. Okay. The question is, find I naught. I'm gonna take a drink of water real fast. Okay. So you could find I naught using a bunch of methods that we talked about, right? Mesh current, no voltage. Oh, we're not going to do that. We're going to solve for I naught using, well, Thevenin equivalent. That's how we do that. Well, before I said that the Thevenin equivalent has an equivalent effect over any terminals, right? So if I call this terminal A, and this terminal B, and just kind of remove that resistance for now, I can find the Thevenin equivalent of, I want to find V Thevenin and R Thevenin, and then I can plot the resistor back in and find the current. That's the goal. So let's do that. Well, let's find V Thevenin. So to find V Thevenin, recall I said we're going to put an open circuit across the terminals. So when we do that, we see that all the current from this current source flows into the 2 ohm resistor. And so using Ohm's law, we can say that, okay, the voltage across the 2 ohm resistor equals the voltage across the open circuit, which equals -1 times 2 ohms, which equals -2 volts. And that is our V Thevenin. So nice and easy. I Thevenin. For I Thevenin, I said, let's draw a short circuit here. When that happens, all the current from that current source goes through the short circuit, and none of it goes through the goes through the resistor. That means that I Thevenin equals -1 amps. Nice and simple in this problem. Okay, so just based on that, we can know that R Thevenin equals V Thevenin over I Thevenin from Ohm's law. So theoretically, this should equal 2 ohms, right? Let's confirm that. Let's do what I said earlier. Let's deactivate all of our independent sources. So when we deactivate this voltage source, it becomes a short circuit. When we deactivate this current source, it becomes an open circuit. And when we combine those and redraw our circuit, we get, here's the open source from the current source used to be. And here are terminals A and B. 2 ohms, 5 ohms, 6 ohms. Let's place a test source. V test. Okay. What's the current through V test? Well, where does the current go? The current from V test goes here. It can't go here because it's open, so it goes down here. It can't go here because there's no way to loop around without going through the exact same branch. So no current flows this way. So it has to flow back out here. So that means this entire circuit can be reduced to V test and the 2 ohms over here. We have I test, so using Ohm's law, V test over I test has to equal 2, and that equals our R Thevenin, which matches what we got earlier, which is good. So we were right. So let's go back up here. We know our V Thevenin. Our V Thevenin we found as -2 volts. We know our R Thevenin. We found R Thevenin as 2 ohms. So what's I naught? Well, what's this resistor? This resistor was R, right? So using Ohm's law, the total current through the circuit, I naught, equals V over R equivalent. This equals -2 over 2 plus R. So what we found is we found that for any resistor, we found the current through the circuit for any resistor that was over here. Very nice and simple using the Thevenin equivalent. Okay. Let's move on. Let's talk about capacitors and inductors. So, what is a capacitor? A capacitor is a circuit element that stores charge between its parallel plates, if you want to get into physics, right? Has some voltage across it, has some current through it. The voltage-current relationship is given by the current equals its capacitance times the time derivative of the voltage. And then solving this, you can find that the voltage as a function of time equals 1 over c times the integral of the current plus some initial voltage from T0 to T, right? The capacitance, emission, and farads. Some things to note. We have a derivative here. If at any point in time we have a singularity, so like the voltage changed instantaneously, that would lead to an infinite derivative term, which is not possible, right? This means the voltage across the capacitor cannot change instantaneously. Other thing to note is that when a capacitor is fully charged, it acts as an open circuit. It allows no current to flow across it. Okay, an inductor. Inductor is sorry. Let's go back to capacitor and talk about how they add and combine. Capacitors add in series and parallel, opposite to resistors. So before, if we had a bunch of capacitors in series, in resistors they just add up, but in capacitors they actually add up like resistors do in parallel. But capacitors in parallel add up like resistors do in series. Let's know. Inductors. Inductors also store energy inside them. They do in the form of magnetic field. They're defined by their inductance. They can also have some voltage and some current going through them. We can say that the voltage across an inductor is equal to its inductance times the time derivative of current, and then of course we get from that current equals 1 over L, the integral of the voltage plus its initial current. So like the capacitor, we see that as a time derivative over here, and this means that the current cannot change instantaneously over time because that would lead to an infinite derivative term. And a fully charged inductor acts as a short circuit. It drops 0 voltage across the terminals and lets all that current flow through it, basically a wire. Inductors add in series and parallel just like resistors. So if we have a bunch of inductors in parallel and series, this the equivalent inductance is equal just the sum of all inductors. And then for inductors in parallel, the equivalent inductance 1 over the equivalent inductance is the sum of 1 over each inductor in parallel, just like resistors. Okay, so what happens when we throw these things into a circuit that consists of resistors and capacitors and inductors? Let's look at the first case. The first case where it's only one nonlinear element in the circuit. So let's talk about the RC circuit, resistor capacitor. This capacitor has a time constant defined as RC, and this time constant tells you how the circuit evolves over time. It gets plugged into equations later. Just know that it's RC. These kind of circuits have two responses, a natural response and a step response. The natural response is when all energy is taken away from the circuit and it's allowed to settle. So it looks like this. So if you draw a natural response, it's going to look like some capacitor. Well, for an RC circuit, if you draw a natural response, some capacitor with some voltage, some R, and some current. Right? These are all going to decay away to 0 after a while because the energy is going to be used up through the resistor. And this response is governed by the equations. The voltage is a function of time. Is the initial voltage across the capacitor times a decaying exponential of negative t over tau, where tau we talked about earlier. And the current is equal to the V naught over R, same thing, e negative t over tau. That's the natural response, and this is the Thevenin, this is a Thevenin equivalent. The step response is where there is some sort of energy applied to the circuit in the form of a source. I'm going to draw it in the best form to use it as. So let's say some Norton equivalent is across the capacitor. Here's I, here's R, and here's the capacitor that the energy is being applied to. It has some V T, and it has some capacitance, and it has some I as a function of time. The voltage as a function of time is going to equal the initial current coming in times the resistance plus the capacitor's initial voltage minus that same term, and then e to the negative t over tau. The current is going to equal that initial current minus B naught R e to the negative t over tau. So the goal to solve an RC circuit is get them into a form you know, and then apply your equations. Also find your initial voltage and stuff, right? Oh, but we have one other nonlinear element, the inductor, right? Let's talk about RL circuits. The RL circuits have a time constant of, oh, I cannot draw that. There we go. Time constant of L over R. The natural response is going to look similar to the capacitors in that some inductor all by itself in series with some resistance with a voltage across it, a current, and a resistor. The voltage as a function of time is given by the initial current of the capacitor times resistance, e is negative t over tau, and the current's function of time is going to equal to the initial current that decays by e to the negative t over tau. And then the step response, this is natural, this is step. The step response, I'm going to draw a Thevenin equivalent. So it's going to be a Thevenin equivalent. We have some inductor over here. Although, I guess, to make it more clear, it's a Thevenin equivalent hooked up to some inductor. Some current and some voltage. Here's some voltage, here's some resistance. So the voltage across the capacitor as a function of time in this step response is given by the voltage coming in minus the initial current to the capacitor times resistance times e to the negative t over tau. And the current is given by, I don't know what I keep writing, S V over R plus I naught V over R e to the negative t over tau. Right. So these equations are a lot, and if you don't want to memorize all of them, you can kind of figure out the first order response of any of these by this general formula. So we have some, let's say we have some output, y of t. It's going to be current or voltage. This is going to equal that value at 0 minus that value at infinity times e to the negative t over tau plus that value at infinity. And using this, you can get to any of these formulas over here if you know how the circuit acts at 0 and infinity. So how do I find those conditions? Well, first of all, to find conditions at infinity and 0, remember the rules talked about earlier. A fully charged, remember how they work when fully charged. And remember that their values cannot change instantaneously. Also, so fully charged, the inductor acts as a short, capacitor acts as an open. And what if they have 0 charge? So at 0 charge, a capacitor actually acts as a short. An inductor actually acts as an open. So using these conditions, you can solve for what these y0 and y infinities can be, and you'll get to this. So if you have trouble memorizing like I do, apply this. So what steps should I use to solve these circuits? Well, step 1. Solve for initial conditions. What this means, solve for before time before 0. Find out what's happening with the circuit before everything starts, before switches start switching and all that stuff happens. 2. Find your Thevenin equivalent. You can find a Thevenin equivalent. I mean, what you really want to do is find the equivalent for the resistance. You want the resistance, really, but you want to find the Thevenin or Norton equivalent around the capacitor inductor. You want a Thevenin equivalent for the inductor, and you want a Norton equivalent for the capacitor. Well, you could solve for either one, then use source transformations, right? 3. ID as a natural or a step response, and then apply formulas. And then you're done. So let's go through some quick examples of this. And I think this is the last topic I'm going to go over because I haven't heard from anybody on if this is what your exam covers. I'm going to assume it is and just stop after this. Example 1. Assume existed a long time before t equals 0. Find the current through the inductor as a function of time for t greater than or equal to 0. Okay, so let's draw this circuit. We have 120 volts. Resistors everywhere. Here's our switch. Here's our inductor. A dependent source. And resistors. So here's I delta. This dependent source is 20 times that I delta. 60 ohms, 100 ohms. This is 0.25 henries. This is 6 ohms, 60 ohms, 40 ohms. And the switch is released at t equals 0. So before t equals 0, it's closed. So following step 1, we want the initial current through this inductor. So before t equals 0, there was some long time. And after some long time, inductor becomes fully charged, right? So for t less than 0, we can redraw the circuit. I'm just going to copy it because it's a small change. That did not work. Okay, we're just going to do the circuit up here. For t before 0, this switch is closed. And for t greater than 0, and for t below 0, the inductor is fully charged, inductor acts as a short. So when it acts as a short, all the current coming from this voltage source flows here and then here, and none of it flows here. Because none of it flows there, this dependent current source, and in fact, this entire side of the circuit gets shorted out. So we can redraw the circuit as this. And here's the short, and here's the I naught we need to find. Where we have 40 ohms, 6 ohms, 60 ohms. You could solve this in a variety of ways, right? You could use node voltage, you could use some clever applications of parallel and series resistances, etc., etc., etc. I'm going to say that if I know this I1, I can use current divider formula. I1 equals V over the equivalent resistance, which equals negative 120 volts, and the equivalent resistance here is 40 ohms plus 60 in parallel with 6, and this equals negative 2.64 amps. And then to find I naught, we apply current division, so that equals the total current coming in times the current division formula. Okay, cool. We found I naught. This is the initial current going through the inductor. Now let's look at t greater than 0. At t greater than 0, we have our inductor, this dependent current source, here and here, and here is I delta, here is 20 I delta, 100 ohms, 60 ohms, and this is 0.25 henries. And we want to find the Thevenin equivalent of this circuit across our inductor. Let's call these terminals A and B. And this comes from up here, our main circuit, right? When the switch lifts, this becomes open, meaning this side is disconnected from the circuit, and we only are left with this side, which is what I drew down there. All right, going back. So let's recall how we found the Thevenin resistance. And we only care about Thevenin resistance, right? We can already tell Thevenin voltage here is going to be 0. There is no voltage. We call open circuit, voltage is 0. There's nothing going through the circuit. So let's find the Thevenin resistance. Applying a test source at the terminals. I'm going to say I have some, V test over here. I delta, 60 ohms, 100 ohms, 20 I delta, and then of course we have some I test going through here. Let's use node voltage to solve for this. I'm going to call this node X. Dependent source internal node voltage, I delta equals negative Vx over 60. Everyone see that? How I got that from? Vx over 60 is the current going this way, and so the negative of that is our I delta. Let's solve for our nodes. So at node A, see the nodes from our circuit up there. At node A, because of the voltage source, VA equals V test. At node B, I test. Well, at node B, we know that the voltage is 0 because we can define that as ground. But I'm going to write KCL at node B anyway, in the hopes that I can use it to solve for the ratio we want. So at node B, I test is minus Vx over 100 minus Vx over 60 equals 0. And we can relate VA and Vx with the voltage source in between them. So we can say that VA minus Vx equals 20 I delta. And this equals negative Vx over 3. And when we solve this, we get that 3 VA over 2 equals Vx. Plugging in to our node equation at node X. Sorry, this is actually our equation for node X, right? Where we define B as ground. That's my bad. We found this equation to try and relate VA and Vx. So when we plug this in into this equation over here, and then we solve for V test over I test, because VA equals V test, we're eventually going to get that V test over I test is 25 ohms. Okay, so we found we found R Thevenin, and we know that V Thevenin is 0. So let's draw the Thevenin equivalent. So across the terminals, we have some voltage of 0. Voltage of 0 is a wire. We're going to have our R Thevenin of 25 ohms. We're going to have our inductor here of 0.25 henries. This is quite obviously the natural response to the circuit. So the formula for the natural response in an RL circuit was that I, the function of time, equals the initial current times e to the negative t over tau. Okay, what is I naught? We solved for I naught up here. We solved for it. There we go. Negative 2.4 amps. So this equals negative 2.4 amps. E, what's tau? Tau for a RL circuit is the inductance over the resistance. So that's going to be negative t times the inductance, 0.25, over the resistance, 25. So this equals negative 2.4 e to negative 100t. And that's our answer. The current of the circuit involved with that. Okay. Let's do one more example, and we'll make it a little tricky. So let's say that we have a circuit like this. Right? Okay. So we want to know the current. We want to know this current, I naught. So the question is A, find current at t equals 0, at t equals 0 and t equals infinity, and B, find I naught as a function of time. And so this is 5 amps, 30 ohms, 0.2 ohms, 0.5 ohms, 100 microfarads, and 1 microfarad. So let's take a look at this conceptually and find what happens. The easiest to find is we can find I naught at infinity. It's an I naught at infinity. Each capacitor has discharged all their energy. And that means the only current in the circuit is from the 5 amp current source. That means I naught at infinity has to equal 5 amps. Okay, well what about I at 0? Well, for I at 0, we really need to know the initial conditions of the capacitors. Let's redraw the circuit to find this out. So, assuming it's been in operation for a long time beforehand, the capacitors are fully charged at time equals 0. That means that each capacitor acts as an open circuit, and we want to find the voltage across that open circuit. The voltage across both the parallel branches, we want this voltage up here. All the current from the current source flows down here. So we can calculate that V open 1 equals V open 2, which equals the voltage across the 30 ohm resistor, which equals IR according to Ohm's law, which equals, this is a 5 amp current source, this is a 30 ohm resistor. So 5 times 30 equals 150 volts. So knowing that the capacitor's voltage doesn't change instantaneously, that means that the voltage right before 0 has to equal the voltage right at 0. And that equals 150 volts. So let's draw a snapshot of the circuit at t equals 0. So at t equals 0, precisely t equals 0, we still have a 5 amp current source. Now the switch is closed. This capacitor is really just 150 volts. And this capacitor is really just 150 volts. And we have I1, we have I2, we have 5 amps. We want this current. How do we find it? Kirchhoffs current law. 5 plus I1 plus I2 equals I naught. We find I1 as V over R. So I1 equals V over R, which equals 150 volts minus 0 over 0.2. And I am defining this voltage, I'm defining this node as ground to aid in my calculations. And in fact, it is ground. I'm defining, if I define this is ground, this is a short, this voltage is also ground, right? So both of these voltages are ground. So I can say I1 is 150 over R, R is 0.2, this equals 750 amps. I can say that I2 is equal to ground minus a negative 150, so V over R equals 0 minus negative 150, because I know that this is a negative 150 volts at this node, over 0.5, and that equals 300 amps, right? So using KCL, I naught equals 1,055 amps. That's perfect. I know the equation at 0, I know at infinity. Okay, now that's part A. But how do I find I naught as a function of time? Especially because this circuit has 2 capacitors and 2 resistors, which is fine if we can combine them all into one capacitor and one resistor, but we can't. They're in parallel branches. They're completely separate. So how do I deal with this? Well, we notice that, well, first of all, when the switch closes, let's redraw the circuit real fast. This is for t greater than 0, so we can see what it looks like. When the switch closes, now we have an open circuit. We have a short circuit here. We have a capacitor here, and a resistor here. Okay. So all the current from the 5 amp current source is flowing into here. The current source does not interact with any of these capacitors, right? In fact, these capacitors don't even interact with each other. Their currents flow over here, but because of the shorts, no cross currents flow. So we can treat each of these branches as a separate natural response. So if I can treat each of them as a separate natural response, I can apply the formulas I know. So here's I1, here's I2. I can say that I1 as a function of time equals V naught over R e to the negative t over tau. Tau is RC. If you remember correctly, this is a 0.2 ohm resistor, and this is a 10 microfarad. This is a 1 microfarad capacitor, I think. Let me go back up here and find. Yeah, 1 microfarad, and this is 100 microfarads with a 0.5 ohm resistor. So when we plug for I1 all those values in with tau equaling to RC, this equals 750 e to the negative 456, all those zeros t. And for I2 of d, we're going to repeat the same process of V naught over R e to the negative t over tau. This is going to equal 300 e to the negative 20,000 t. And then when we use Kirchhoffs current law, we find that I naught as a function of t equals 5 amps from the current source plus 750 e to the negative that means zeros t, and then plus 300 e to the negative 20,000 t amps. And then that's our answer. As a double check, using this equation, I0 of 0 equals 5 plus 750 plus 300, precisely what we got earlier. I0 of infinity equals 5 plus 0 plus 0, which equals 5. Check marks, it matches up, right? Yeah, assuming you guys stop there and that's what your test covers. the review is over. So good luck on your test, and thank you for coming or watching, or whenever you decide to watch.